Learned something. Windows DisplayPort dongles don't work with a Mac. Now we're okay. What? Stop heckling. That's for later. Oh, I said dongle. I'm sorry. To start off with, since I'm the last talk, I wanted to give a cheers to the BSides organizers. All right, we're here to talk about solid-state disk drives. Solid-state disk drives are the new way of us having storage instead of having a spinny drive. And they behave in a different manner than our traditional hard drives. So what I want to do is explain to you how these drives work, how they differ, and what that means from a security perspective. To start off with, I am Michael Zapp. I am a senior instructor at the Department of Computer Science at the University of Manitoba, blah, 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 blah. And it's been weird. Because I walk into this room and I see so many people I recognize. And I have to apologize because I don't remember your names. But I remember all of your faces. It's like, yep. So I just wanted to ask, how many people here have I actually taught?
Right here.
Holy, that's pretty awesome. What? Once again, cheers.
It's an intervention. We're here to tell you you're a dog.
I like having pictures on my slides, and I thought it would be stupid to have a picture of myself, so I have a picture of my dog. Seemed legit. I have a really small email address here, zapp@cs.umanitoba.ca. The other thing I wanted to mention is we, the Department of Computer Science, about 3 weeks ago, finally started a Twitter feed. It's at U of M CS. Okay? We actually tweeted BSides. How do I know that? I run the Twitter feed. So anything you see there, that's me saying it. Scary, but true.
Posting due dates? Assignment due dates? Reminder?
Yeah, no. We have, no, I'm not going to get into that. All right. In addition to being a teacher, I've done a lot of other work, and I thought it was worthwhile to mention some of those things. I spent roughly a decade, give or take, working on electronic control units, doing embedded software, mainly transmission controllers. So when you're driving your vehicle, the software that shifts gears for you. I worked on that kind of stuff. Probably not for your car. Don't worry about it. You won't die because of me. Somebody else will do that for you. In addition to that, I do consulting work. I'm willing to be paid to develop software. It's a strange concept. One thing that you may have experienced with respect to that is if you've ever driven a go-kart. There are 2, maybe 3 different engine controllers for go-karts in the world, and one of them is mine. I wrote the software for it, so if you're actually driving a go-kart and it limits your speed, I did that. Yeah, I could tell by all the hands that I was screwed one way or another. In addition to that, I've written software for friends and acquaintances of mine that have ended up gaining a life of their own, and they're actually sold. And I have an icon for one of them over here. Oh, it doesn't show the cursor there. Fine, whatever. North. That one in particular, the reason I brought it up there is you have friends that ask for things and they happen to be influential and you kind of do it. That was software I wrote to make ebooks. And the reason I made it is I had a friend, and I won't name drop, but he's the author of a book called I, Jedi, if you've ever read it. He wanted to do ebooks, and I helped him and wrote software to do that. It was easy, and I make money doing that. It's kind of fun. Having said that, for me, I prefer living here. Oh, here. Jeez. Hardware is where it's at. Hardware is fun. An operating system, yeah, operating systems are okay if I get to write them. Anything above an operating system, boring. I don't like it. Not me. You can like it. Hey, you want to write database code? Go for it. Last thing I want to do is write a web app. Boring. Not for me. Okay? I'm not going to talk about that stuff. I'm going to talk about down here. You did that in my real-time class. I remember that. Yes. There are certain things I remember about certain people. You did that before. Exactly around the same time when I was giving the same style talk. Now, we're here to talk about security, and you should be going, okay, wait a minute. Where in all my credentials did I talk about security? I didn't. Okay, sorry. I don't really have security credentials in terms of you guys. You guys are much better at it than I am, some of you. Having said that, I actually teach the security course at the U of M, which I conclude with, ooh, all right? I'm a security expert. I teach the course on it. I must know what I'm talking about. Thank you. Not when I taught it. No. It's much better now. The goal that I have when I teach the course isn't to make a computer security expert. It's actually to go and tell people that they have to care. It's amazing how many people become software developers and don't care. Security doesn't matter. I don't need to worry about it. Not my application. And they end up writing the code that everybody gets to exploit. So the goal of this course is to say you have to care about that. That's about, jeez. I hate this microphone, just so you know. Ugh. What's that? Microsoft. I don't know. So I'm not a security expert. I'm willing to admit that. I will never be a security expert. I think it was Ian that said what felt like this morning, if you actually say you're an expert, you're wrong. You were much more colorful than that. But I'm willing to admit that. What I care about is making sure that people have as much knowledge as they can. If you want to be able to make something that is secure, or if you want to be able to exploit the security of something, you need to understand it inside and out. All the details, every little piece, you need it. And that means getting your hands dirty. And there's nothing wrong with that. That's what makes life interesting. If you've had me as a teacher, you know I tend to focus that way with everything I do. My goal is always make you guys the best. Some of you, yeah, not you, Steve. No, not you. Yeah. You sitting up front, you're just screwing yourself. But of course, you're distracting me too, just like you do in class. So anyway, getting to know the nitty-gritty is what life's all about. And what I want to do here is to talk about not just solid-state drives, but flash memory in nitty-gritty detail, to know as much as we can about it. In the next 50 minutes, you're not going to know everything, but hopefully you know enough to then go and want to learn more. So if we're living at the hardware level, we have a different set of tools. And I want to spend just a little bit of time talking about them. There are a lot of different tools. Some of you, minority of you, have gone through engineering and you've used all of these tools. The majority of you haven't. We start at the level of a scope and a single signal generator, even an in-circuit emulator. Things that we can use to probe hardware and do hardware design and things of that nature. Now I'm understanding the reason not to have a beer while you talk. Excuse me. All right. One of the key tools is a logic analyzer. Excuse excuse me. This is just a simple, basic, you can buy this for a couple $100. It's a logic analyzer with, I think, 16 probes. You hook it up through USB to your computer, and you can look at waveforms. Okay? So each of these is an individual input that you would then probe on a bus line between chips. You can actually group them together to say the address going between these two chips is currently a given value. Okay? You use this to try to figure out what's going on. If I have a piece of hardware and it's running and I have no idea what communications are going on, I can hook up a logic analyzer and start watching the data going back and forth. That's fun. Being able to see that, really cool. The next level tool is something called JTAG. JTAG actually stands for Joint Test Action Group. Boring, JTAG. JTAG was first created just for testing hardware. If I built some hardware, I want to test it, I use JTAG to do it. Very quickly, it became how we actually debug hardware. So if I'm developing software at the hardware level, I will use JTAG so I can actually analyze what's going on. JTAG provides me with the ability to do all standard debugging. I can step, I can inspect memory, all of the kind of things that you're used to doing with a source level debugger, you can do with JTAG, but you do it on the chip. Okay, you're actually connecting to it. And over here, this here is just a USB connecting to a header. This is what you will find on a standard circuit board. Somewhere there will be probe points for connecting a JTAG interface. Everybody has it. If you pull your phone, it's usually a nice small little circuit, but there will be a JTAG interface so you can plug in and get it. The first jailbreakers on an iPhone were doing it at the hardware level. They were doing it through JTAG. It lets you get in. Not only can you trace the activity, you know exactly what's going on. No, I got...
Yeah.
Best talk ever. All right. Shall I have some water? Okay.
I have to edit your voice later. I have to listen to it in my ear.
You're inspiring me to do worse. All right. In addition to being able to step and breakpoint and do all of that, through JTAG, I can also control all of the I/O pins. So if I have JTAG access to a chip, I can control all of the I/O going in and out. And I can, therefore, gain full control of the bus. Say I have JTAG to the CPU, I can control the bus. If I have JTAG to another chip, I can manipulate that chip in any way I want. Okay? It is a very powerful debugging tool, but also allows us at the hardware level to do whatever we want. We like JTAG. JTAG is the tool. It's going to be a long night. We can go till 8, right? 8 o'clock? 7? Everybody will help. It'll be a communal thing. It'll be an Amish thing. We'll do it together. All right. Ian's inspired me. Let's talk about flash memory. First of all, thanks to whomever put this on Wikipedia. It's a great picture of a single bit of flash memory at the transistor level. Flash is all about individual transistors that hold their state when there's no power applied to it. It's actually quite simple. You have a source line and a bit line. The source line is attached to ground. Whether or not you complete the circuit depends on the gate. And the position of the gate, is the gate floating or the gate connected. Simple enough. I don't know more than that, so hey, I'll stop there. When we erase a piece of flash memory, it is set to 1. So any bit of flash, you erase it, it becomes a 1. If I want to write to it, I can set it to a 0. I cannot, however, write to it from a 0 and set it to a 1. I have to erase it. Okay? Those are the rules. I have to live by those rules. Nothing we can do about it. Reading from flash memory is really fast. Writing and erasing is slow. It's faster than a hard drive, but it is slow relative to a read. It will take 4, 6, 8 bus cycles for a write to complete. Writes are slow, erases are slow, so we want to avoid erases because they're slow. And this comes into play later on. We have 2 forms of flash, and hopefully I will have enough time to talk about both of them, but I'll make sure I talk about NAND flash, because that's what's in an SSD. There's also NOR flash, which is something much more interesting, but save that for later. They have physical differences, but the main difference between NAND and NOR flash is the fact that NAND flash doesn't have as much memory logic associated with it for addressing in. So it has different behavior, and they made that decision because it's cheaper that way. Without all that memory logic, they can make cheaper chips, they can optimize for disk-style access, and we now have tons of NAND memory because they made that decision. In addition, the memory inside of a flash chip is organized by blocks, and they may be 4K up to 512K blocks of memory. And the reason that's important is I can write a word into flash, but I can't erase a word. I have to erase the entire block due to physical characteristics, blah, 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 blah. Physics. All right, so we have to erase a block, we don't have to write a block. That's useful. Not quite so useful is that every time we do a write and erase, we're moving this gate. And there are chemicals involved in that, and it's a physical device. And every time we do that, we, quote unquote, burn off some of the chemical, which means eventually we use it up. It doesn't work anymore. At that point, whatever that bit was fixed at, that's what we get for life. If it's a 1, it's a 1 forevermore. If it's a 0, it's a 0 forevermore. Okay? If we like it being that value, we can still use that memory. It now becomes ROM. That's fine. If we want to update it, we have a bit of a problem. Okay? This is usually on the order of 100,000. We can do 100,000 of these erase cycles, and then it's done. All right? So that becomes, at the physical level, what we're dealing with and what we have to worry about. All right? Next thing I want to talk about, just building up from the low-level hardware and all the way up, is we have the chip. This is an actual NAND flash chip on a circuit board. Okay, I'll explain the arrows right away. The pins, I'll get to being specific as to what's on a NAND and what's on a NOR shortly. But what we have, oh, that's too small. We have address and data lines and control lines for manipulating that. All right? What we then can do is we can use our JTAG to control CPU to start need beer. No, beer. Which is another weird thing, right? Prof drinks beer. Who knew?
I always thought you were Amish. Beer.
B. So I can control the CPU and mess with this flash chip because I can control all of those lines to my heart's content. In addition to that, nothing. So there we go. All right. If you're going to say something, see, I'm used to being in a classroom. If you want to talk, share with the class. That's good. That's good. In addition, some flash chips will actually give you a JTAG interface. This chip, these arrows, those are the actual JTAG lines for this chip. What they give you that for is so you can write to it and read to it. So you can program this chip if you wanted to. But that also means, from our perspective, if I want to do some fun stuff and access the data on this flash chip, I can do it directly. In fact, I can take this off of the circuit board. I don't need the circuit board. If I can drive it, give it power, and have the JTAG interface, it's mine. Okay? I can do whatever I want to that chip. Fun. All right. Yes, we're going with a low level here. This is NAND flash. Why is it NAND flash? Actually, it's pretty simple. If there's an engineer in the crowd, they can explain it like that. It's a wire AND. You have individual cells that are connected to one another. They're ANDed. Okay? That's the physical characterization of a NAND cell. Okay? We're just ANDing them together. And this is the basis for all of the SSD memory that you use. There's a bunch of these. Okay? At the lowest level, that's what it contains. We cannot do random access to this thing. Okay? It has a disk drive interface. Like I said, it doesn't have any of that logic that we want so that we can interface to it and address individual words. But we can do page transfers. Exactly like you would do with a disk drive, you can do DMA transfers from an SSD into your RAM and from your RAM to SSD, but we'll talk about that shortly. All right. This is how we actually organize the complete SSD. What we're doing here is we're taking the individual NAND chips and putting them in an array. For RAM. It's exactly the same organization in that we have a number of individual blocks on each chip. So we have individual chips. They have a number of blocks in them. And then what we do is we overlay pages onto that. Okay? So we have page 0, page 1, up to page P, N, whatever. Okay? And this is how we store the data on the SSD. And this is important. This actual organization and the implications of that organization are really important to us. But it's done just like we would if we were doing virtual memory, paging in and out. We have individual pages stored on flash, nice and simple, efficient, exactly what we want it to be. Okay? Moving up a level. Didn't think you'd see a chip. Just wait. It's about to get like a class. This is the standard pinout for a NAND chip. There is a standard, I can't remember the name of it, for all NAND chips, so you can buy a NAND chip from wherever you want. They're all going to look the same, have the same interface, and be manipulated the same way, which is very nice. I can source it from anywhere. So in this diagram, which you can't read, the pins are really, really small, sorry. It's not my fault, it's their fault. They need a better projector. Ooh. So what we have here is we have a bunch of I/O pins for sending data back and forth. We also have pins, I guess I'm going to have to carry this. Yeah. We have read enable, chip enable. We have address latch enable, we have command latch enable, and I'm going to explain all of these in gory detail. We have a write enable, we also have a write protect, and a write protect is quite simple. If I drive that line right there, pin 19 low, you can't write to that chip. No one's allowed to write to it. Okay, so I can physically prevent anybody from writing to that flash. All of these lines are all the I/O for data and address and things of that nature. Okay? So if we want to hack this chip, we have to know how to talk to it. Okay? At the physical level, we have to have some kind of understanding. We have all of these pins, so what we need to do is understand the basic protocol for talking to it. And if we want to talk to an AND, there's a just basic general operation. You latch a command, you latch an address, and then you do your operations. You read or you write. Some of the commands may be things like an erase, which is different. We won't have to read or write. But the first thing you do is you latch the command. So what we have here is the command latch enable, the write enable, address latch enable. The timing of these signals are all for setup. to say, we are going to give you this information. And we have a different sequence of signals for everything, different thing that we want to do to the chip. Then on the command lines, which is the bottom 8 I/O lines, we specify just an 8-bit command. Read, write, erase are the standard commands. The last thing we have here is we have a ready or busy bit. And this here is this is driven by the chip saying, I'm busy. You can't do anything. Every operation you perform on flash takes some amount of time. It's not instantaneous. This bit tells you when it's done. So if you put a command on there and don't wait and then you give it an address, if it's not ready for it, it won't work. Okay? After you've given a command, then what you want to do is give it an address. So again, this is a standard protocol. All NAND chips do it. The timing might be different, but the protocol is the same. We have a number of bits here. Command latch enable, write enable, address latch enable. Again, we do a specific sequence, give it an address, and it will, in this case, not worry about ready because it's already ready. Ready already. Raw. Cheers. It's ready already. All right. So now what we can do, and I just picked a write. I could have done a read as well, but I figured one was enough, is once it's all configured and everything's ready to go, we just keep going. And if you actually look, well, too far, but from here, these timing diagrams just continue on to the actual write, because these lines stay low, and then we start toggling. And we just toggle the write enable for each actual word that we're writing, and we can have any sequence of writes to it. Okay? That is how we actually talk to a NAND chip. If you give me a NAND chip and I want to start reading or writing to it, this is what I have to do. Okay? That's now above the physics. We've got the transistors, we've got this protocol that we can talk to it. At the next level, we have to take into consideration how a NAND chip behaves and what effect that has on what we're doing. Okay? So if I can talk to it, I can start pulling stuff. Where do I look? I want to get data off of this NAND chip. How is it stored? How is it configured? Well, the first thing that we have to worry about and understand is the idea of wear leveling. Okay? If you recall, we only have 100,000 erases. Because of that, we want to make it so that our chip lasts longer. And the way we do that is by saying, I never want to erase something that I am going to update. So in this example here, if I have dead beef and I want to change it to 8 dog food, what I will do is I will read dead beef from memory into RAM, update it, and then write it back. But I will write it, and I just noticed the 01010 is invalid. It should be all ones. Sorry. Ooh, invalid slide. Error. We write it to another location, maybe the next location on flash. This is the basics of this. And we do that so we don't have to erase this. We don't want to erase it because that screws up our entire block. Why? I have to erase the block. I can't erase this word. The whole block goes. Then I can overwrite it, which means all the data around it has to be overwritten as well. So I need to copy all of it in addition to that. So the solution we have at the fundamental level is we never overwrite data when we update it. We write it somewhere else. What happens to dead beef? It stays. It's still there. Your previous data will remain. Okay? You have to think about that. All right. We're going to go into how the operating system handles this later. What I want to do now, though, is give an example. And the example I'm going to give, I took straight from TrueCrypt, because they had a nice little security advisory regarding wear leveling, so I'm going to use it. If you have an encrypted volume, you have a password. That password is stored at the volume header. And that volume header is then encrypted to protect that. If your password is compromised, you have to go in and update that password. What TrueCrypt does is it will take that password, encrypt it, and write it back to the volume header. Same location. That's how it's defined. So then it can be pulled out afterwards. If it's on an SSD device, it did not overwrite the existing volume header. It went to a new location because wear leveling is involved. If I get a hold of that chip, what do I get to do? If I know where the volume header is supposed to be, which I can probably figure out, and I just have the chip and I'm using JTAG to play with it, I can, of course, take the compromised password, previously attained, you went and changed it, I can use the compromised password on the old volume header to decrypt that volume. It's all available to me because of wear leveling. It's a bit of an issue, maybe. See, I'm trying to go over here. So now the question is, how do we solve that? How do we deal with that problem? Well, there's one simple solution. Simple is always erase it. Always erase old data. Screw wear leveling. I don't want to wear level. I'm going to make sure that my protected data is always erased. To do that, I need low-level driver access. All right? I have to worry about getting that control. The operating system isn't going to do it for me. I have to write my own driver. Then I can guarantee that it's always erased. Of course, if I always erase it, wear leveling goes out the door. So are we allowed to make that choice and say, nah, we don't need wear leveling? Well, we do the math. It's a cost issue. How many times am I going to overwrite this data? How long does that give me for my life? When do I end of life this part? Do I end of life it in 5 years or 10 years? Is 5 years okay? Is the extra cost of it dying early worth it to me? If I can make that decision, I can say, fine, wear leveling, screw it, it's not worth it to me. In the general case, wear leveling is happening all the time. If you have a device with SSD in it, wear leveling is happening. It's even happening at a higher level. Having said that, if I'm not willing to make that choice, what's our other option? Well, our other option is encryption, because encryption solves everything. Thank you. That was supposed to be a joke, so thank you, Ron. 15? My clock says 27. Well, no, that's when I started.
How much longer are you talking for?
2 hours. Yeah. Well, I'll just be part of the band. Is that okay? The band. I could have a backup band. That would be cool. Encryption solves everything. If we can encrypt it, hey, life is good. Okay, so what we now have is every modern SSD that you buy has hardware level encryption turned on automatically. You have no choice. It is there. Everything is encrypted for you. That means, of course, that what we get is that problem with the volume header. We don't have to worry about it because we're not actually doing that. It's burnt into the hardware that everything is encrypted and etc. And we're good. Yay, life is done. Right? We can walk away. Yay, yeah, get up, go. Yeah. As you go up a level, you realize that the operating system does some other stuff for us. Not just the operating system, but the actual SSD device does extra stuff. We've been talking about it at an abstract level, but what we have in the SSD is we have a drive controller, a disk drive controller that manages all this stuff. Then we have our driver in the OS, and then we have the OS itself. And all of these things are doing stuff for us. So we have the SSD controller. What does it do? It wear levels at pages. Not at blocks, but at pages. Remember we had this, oh, here's a page across all these blocks and all these different chips. What it will do is ensure that if you update make any update to the page, we are going to copy that entire page into a new set of blocks. Okay? Whole thing. So if I have a 4K block, a 4K page, all those blocks come along. Just to update one word, we're going to do the whole thing. And that's what the controller does for it. It then comes along and says, all right, oh, I did forget the one important reason. Why does it do that? It doesn't want to wear level a single block because then you get all of your blocks out of alignment. You have page 0 on block 0. Oh, except for that part. That's on block 1. That kills our performance on DMA transfers. So we want everything on block 1, not just one block of the page being block 1 versus block 0. So we do want to do it for optimization purposes, not for security purposes. Then what happens is the SSD controller, when everything's idle, when we're not accessing the drive, it goes along and garbage collects. And it finds old blocks and erases them for you. And the reason it does that is because erases take time. Because erases take time, we have to come along and wait for an opportune time to do it. The ramification of that, your old data is residing on the solid state drive for an indeterminate amount of time. Okay? You have no idea when it will go away. In addition to that, you have to realize that operating systems don't delete files. They mark it as deleted. It doesn't go away, it just says, that's an invalid file. If you try to read from that file in the future, you get an error, that file doesn't exist. That file definitely still exists on the drive. What does that mean? It means if I come along, modify a block of my page, and then it does wear leveling for that modification, it copies the entire page out, puts the entire page in a new set of blocks, including all of the deleted files. So now not only do you have old data residing around, you have potentially multiple copies of deleted files scattered throughout your drive. Isn't that what we want? Yeah, thank you. Yay, life is good. It's exactly what we don't want. Okay, so we're in a position where we have old data and deleted data polluted across our drive. Awesome. If we want to get old data and deleted files, we can get it. So now the question comes, how do we solve this? What can we do? And this is where we actually bring the operating system into it. Okay? The operating system has no control over when an SSD garbage collects, when it wear levels. That's all done by the drive itself. Okay? But what we've added to SSDs is the trim command. Okay? And what the trim command does is it allows the operating system to tell the SSD which blocks are invalid. Okay, so if I delete a file and that file is across these 3 blocks, the operating system can say those 3 blocks are no longer valid. Okay, they still exist there, but they're no longer valid. What that then means is that the controller can skip those blocks. When it does the wear leveling and copies it over, it'll say, oh, those blocks are invalid, I'm not going to copy them. Great, awesome, good. We don't have to worry about polluting deleted files across. Having said that, the SSD isn't doing that for security purposes. It's doing it as an optimization. It speeds up because I don't have to copy all of those blocks to memory and then write them. Each write takes some amount of time. So if I can skip half of the blocks in the page, when I write to it, it's twice as fast, theoretically. Okay, so we actually get optimization. We get to the point where we hope that we only have one copy of a deleted file, that is the current one. It's not anywhere else. It's not copying. It's the one that initially existed, sorry. All of the copies aren't copying that file over. This is provided to us in Linux as of 2.6.28. But it's off by default. You have to actively go in and say, I want trim. And we'll explain why shortly. With the Mac 10.6.8, but only on SSDs that are manufactured by Apple. It shouldn't be a surprise in any way, shape, or form. If you do a third-party one, there are tools to activate trim on that, but if you don't do it, it's not going to do it for you. Windows 7 added trim support. So if you're still using Windows XP or 98, as I heard someone say earlier, how freaky is that? Understand. Yeah, Windows 98, rock on. It does Android as of 4.3 has trim support. Prior to that, there's no trim available. So your old phones that they're not being updated or whatnot do not do trimming for you. Okay. Having said that, the question does arise whether or not you actually need trim on your phone. You need it if you have an SSD controller. So if the phone is built like a standard computer, then absolutely. iPhones don't have trim. The reason they don't have trim is because there's no SSD controller. Apple has a custom, which they won't tell us what it does, how it works, but they manage all the wear leveling themselves, and we have to trust them that everything is cool and that they do everything intelligently. Again, it's exactly what you'd expect them to do. So there you go. This does raise an interesting question, though. If I'm doing this and I'm not copying over those deleted blocks, what do we actually get there? Okay. Now, of course, we have encryption, so we shouldn't theoretically care. Everything's encrypted, everything's locked up. But if you would actually look at what you would pull from a number of blocks, you would get something like this. You have a bunch of ones. What's that? It's erased. It's never been written to. You have the actual data from that page. Then you have a number of ones as well. So you get all of this stuff. And what is this? It's a pattern. And we should all know that patterns become useful. I wasn't sure if that was a question or a thumbs up. Thumbs up, good. Anytime there's a pattern in the data, I know I can get an idea of what's going on. Okay, this is telling me, okay, I'm gonna have to skip a big chunk.
Just like a cat does when it walks on the keyboard, you get the same.
Yes, meow. So from this, as we're wear leveling, I'm seeing the holes where data was. I'm seeing which parts of a page you're deleting. What is the stuff that's being updated on a regular basis? What is the stuff you no longer want to have on the drive? That's information. We could theoretically write this, right? That would be to put random data in there. But then, of course, we're defeating the purpose of the trim, although I would argue from a security perspective, the random data is better than a bunch of ones if we do it properly. Having said that, if we don't do this, we also have something that would probably, I've wondered if, what? What? Wow, time warp, man. We just went from 5 minutes to 15 minutes. I feel like the Doctor. Whose TARDIS was that? Jerk. All right. The other aspect of this is the notion of plausible deniability. This is something that I would figure someone like Ian, having just met him a day ago, is someone that would really, really, really want plausible deniability. He's not even paying attention. He's done? He's just, okay. Awesome. The fact that we can show where we deleted files and what operations we were performing tells us you had something you didn't want us to know about. Okay? That can be a problem depending on what you don't want people to know about, and we won't get into all that stuff. Hi, Steve.
I have a question.
An actual question?
It is. So if you can only write zeros and erase ones, how do you come up with 3 A, E, 2, C?
Oh, you don't write those bits.
Are
You
those
wait.
bits or letters in the alphabet?
This is hexadecimal.
So then every one is actually a 0, 0, 0, 0, 0, 0, 0.
You can stop now. Each of these is 4 bits. Don't worry about it. Yeah, I should have. Actually, now that you ask that, I should have done F's there. Yeah. Oh, yeah, I'm sure you were, Steve. Yeah. Yeah, just throw away the entire talk. This is wrong. We're done. Okay, have a good time. Once again, TrueCrypt actually advises that you do not store your data on any solid-state drive that employs trim if you want plausible deniability, which is why Linux by default doesn't turn trim on. If you want that, then you turn it on and say, yes, I want that. By default, they're erring on the side of, you may not want that. Yeah.
I heard that ext4 did turn trim on.
Okay, different file systems. You know, I actually looked at the whole list of which ones turned it on and which ones didn't turn it off. ext2 definitely does not turn it on. ext4 may just turn it on, and yeah, that you'd have to look it up to be sure. I'd have to look it up, and I'm not going to do that now because I have negative time left. So what I was going to do now, that's SSD issues. What I wanted to talk about, and I just do not have enough time to talk about it, damn it, is NOR flash. It's all your fault, Ron. NOR flash, as you can see, we OR the bits together. NOR flash is all about storing executable code. Okay, and the reason that we do that, so all your firmware on your phones is stored in NOR flash, not NAND flash. We actually have 2 types of storage in every device. And I'm going to do this fast, unfortunately. This is a memory map, and what we do is NOR flash is actually mapped into the CPU's address space. So we can address, just through pointers, into the NOR flash and read it word by word. We don't have to do disk transfers, we get it right away. Okay? So that means that I don't even have to copy my code into RAM. What we will do is we will have our runtime stack in our heap in RAM, sure, but the actual text and data areas of our process stay in flash. Okay, so that means I need a smaller RAM footprint, okay, which is good, but it also means that I get really fast reads on it, but I get really, really slow erases and writes. It's much slower to erase and write NOR than it is NAND, because it has all this extra memory logic to handle that, okay? The glory of that is when we have firmware, I don't really care about updating too often. When do I update? When I do an OS update. When you do an OS update, you actually see exactly what's going on because it resets and reloads the firmware. When it's doing that, it's writing to NOR, okay? Prior to that, everything's in NAND, then it's in NOR. The standard execution model is we boot up, we load location 0, it's just where it starts. We load location 0 into RAM, we determine what to do, and the next logical thing is to jump to the next block. That block will contain a initd or whatever for your operating system, and that will then get loaded and start executing. Normal behavior, nothing strange. If, however, On startup, the CPU detects that we want to update our NOR flash, some kind of wires, signals coming to it. What it will do is it'll actually continue executing in this block. This initial block is called the boot block. Okay? Most of the time, it never executes. It just jumps to somewhere else. The reason we have the boot block is so that we can have special functionality when we want to update NOR. Okay? So what this code is just code to write to that. Okay? And that involves the use of a bootloader. And I'm going to give you the simplest bootloader possible. This will be proprietary to different devices. They will have different handshaking and different things. But what a bootloader tends to do is it just erases all the blocks on the NOR flash. Then it reads, oh, that is tiny. Holy crap. Come closer. Yeah, even then. Yeah. See, Mike's leaving because he already knows it. Right, Mike? You've seen this before, right? Yeah, all right. So I've erased everything. Then what we have is we have the actual new code that we want to put in the NOR. And this here is Intel hex format. There's two formats. There's Motorola S records and Intel hex format. And it just has record length, start address for where I want to write, what kind of record it is. It's usually data, the actual data, and a fancy-dancy checksum at the end. Okay, so we can verify each line. What a device like a phone will do is it'll download a new copy of the firmware. It'll copy that into NAND, probably. Then it will do a verification. It'll do some kind of authentication handshaking to verify that this is valid code. Then it resets, starts executing the bootloader. The bootloader will then go to a known location in NAND and start reading this and writing it to NOR. Okay, again, this is simplified. In the end, the bootloader is really simple, doesn't do much. It just writes the stuff and says everything is cool. Okay? It assumes that. So when you jailbreak a phone or want to do anything to update the functionality of a device, you just have to get the bootloader to run and to recognize your code that you want to write to NOR, and you can update it to whatever you want. Okay? Now, this here is something that I am doing this next part, and I'm glad you extended. This is just for Mac, because Mac wanted me to talk about hacking cars, and this is just a small part of hacking cars now. One of the really, really common, easy things that you can do is you can download new firmware for your ECUs for your car. One of the things that a lot of people do is they'll put in new shift tables so they can up the rev. Right? And then they can go cruising up and down Portage being cool, right? If you do that, awesome, you're cool, honest. How that works, I could theoretically do it if I had access to the chip, the CPU, just fine. But every complex embedded system has a network, okay? It'll actually have a bus that connects all the devices in your car. And there's a diagnostic port. But it's not just a diagnostic port. If I plug into there, I can update the NOR flash on each device. The way it works is there are standard protocols. You can look them up. Well, there are standard protocols, and then there's the manufacturer-specific ones. If you go to URL, I wrote it down somewhere, and I can't find it. Standards.sae.org. SAE is a Society of Automotive Engineers. Under automotive, there's a bunch of protocol standards and other things. The one of interest, well, there's a few, but the one that I'm most familiar with and is used in all construction vehicles is J1939. And that gives me, I think it's like $700 to become a member, and you have full access to all of the standards that they use for all vehicles. Okay, go for it. Fun. They will have in their network protocols a means of talking to each device to reset it and start sending these Intel hex records as packets on the network. And these things are not secured at all. They're secured by the fact that you need a special header to plug in to the car. And the only way you can get that is if you're actually working at a service dealership, right? It's impossible to get one any other way. At one of the companies I work with, one of the products we made was just an adapter module. And it handled half a dozen different protocols. You plugged it into the vehicle, you plug the other end into your PC, and you're watching all the network traffic, and you're talking to every single device. And one of the things that we used that for was for servicing. So we updated the flash on them. And we can reprogram any vehicle to do whatever we want. Lots of fun. And these things aren't secured at all. At all. All right? And that's where I will end this talk.